My presentation has to do with the deep potential method that we developed in the past few years in collaboration. Let's see, does it, why doesn't, oh, here, maybe I have to go here. Okay, in a collaboration with Waynan, and I must say that most of the work, the driving force behind all this development has been Lim-Fen Zhang, who was a fantastic graduate student. He just graduated a month ago. And we are still collaborating with a lot of stuff to complete, and really was a great pleasure working with him. So in this approach, we are essentially using deep neural network to solve the molecular dynamics problem based from DFT, density functional theory. So we are not looking at absolute accuracy in solving the many electron problem, but we are looking at solving problem that can be done with molecular dynamics over a large size and time scale. Let me discuss. So essentially, we want to overcome the size and time bottleneck of ab initio molecular dynamics with deep potential molecular dynamics using neural network representation. This picture is just an illustration of the fact that we can deal with rather small system, and with the neural net, when we do ab initio molecular dynamics, and we can do only a limited number of frames, so a small time scale, but we can increase quite a bit on the size and the time scale when we use deep neural network without losing accuracy. So I will discuss in general in this approach, we represent an observable. The observable that I will consider in particular will be the potential energy surface that describes the interaction among the atoms in the system, and also the polarization, which is a vector quantity, and I will mention that we can also extend to polarizability, which is a tensor quantity. And we use essentially the same kind of representation for all these quantities. So what is interesting is that while the potential, the electronic information has been coarse-grained out when we consider the potential energy surface, when we consider the polarization or the polarizability, there is explicit electronic structure information that the neural network has to carry about. So essentially, the neural network, in the neural network representation, we write an observable as a sum of local observable, where each one of these local observables depend on a suitably defined neighborhood of a site, I, for instance, and it includes all the atoms in this information on the many-body dependence of this quantity on all the atoms in this environment. Now, the function f that is represented in terms of neural network must satisfy a certain number of symmetry, like the translational, the rotational, and the permutational symmetry among atoms of the same species within the environment. And should be also a continuous function of the atomic coordinates in the environment that may have a variable number of atoms as the simulation proceeds. Well, this property can be ensured by combining, by using a technique in which we combine two deep neural networks an embedding neural network that essentially is a property that is invariant with respect to all the symmetry that I mentioned before, and that contain essentially the descriptor of the atomic environment, and the fitting neural network that gives in output this function f, and where f can be a scalar, a vector, or a vectorial, or a tensorial quantity. And these two neural networks are optimized simultaneously. Let me just move here. So let me just discuss how we do that for the polarization. I give here the references where all these procedures are described in detail. Now, in order to represent the polarization, we need to know we need to have information about the electronic structure. The information about the electronic structure is provided by the Vanier centers. So the centers correspond to the distribution of associated to the maximally localized Vanier functions that are obtained from a unitary transformation of the occupied orbital subspace. In an insulator, we are dealing here with insulating systems. And for instance, if we consider, for example, water, and I will show a few examples related to water. In water, the Vanier centers are associated to the oxygen atom, and there are, so to one atomic species, and the coordinate of the Vanier centers are indicated by this Wi, but since there are 4 Vanier centers with 2 electrons each, we are considering a spin-saturated system. We consider the Vanier centroids, that is just given by this average over the position of the Vanier center associated to a given oxygen atom. Then we go to find this representation of the Vanier center from the coordinate of the atom in the environment of the oxygen atom to which the Vanier center of the Vanier centroid is associated with. And this is done via several steps in order to satisfy the 3 symmetries that I mentioned before, and in order to define an important feature that we want to obtain is that the neural network representation that we obtain is an end-to-end representation. There are no hidden or parameters other than the coordinates of the atoms and the network itself. So first we go to a local frame for each environment in which we refer the coordinate, this prime coordinate, to the coordinate of the atom that is at the center of the environment. That in that way translational symmetry is automatically satisfied. Then we have to define the descriptor of the coordinate for the atoms. Now the descriptor, we want to have descriptors that give more weight to the atom the closer they are to the central atom, and also we want to obtain a formulation that goes that is continuous as an atom enter or exit a given neighborhood. So what we do, we represent the coordinate by a 4 vector, this q, ki, in which we have a fixed weighting function that is this s that decays like 1 over the distance in the bulk of the environment. But when an atom gets close to the boundary of the environment that is defined by a cutoff radius, this fixed weight function goes smoothly to 0. The ensemble of all these atomic coordinates constitute a matrix Q, that is a matrix with 4 rows, the 4 components of each one of these vectors, and a number of columns that is equal to the number of atoms in a neighborhood. And then using that, we can define an embedding network. The embedding neural network is given by a matrix. Here there is some typo in this thing. This index I should not be confused with the index I that entered in the R prime of Ki, that is the dependence. So this is the essentially, with this network, we go from the atoms, information from the atom in a neighborhood to M outputs. M is a number that is fixed by empirically by studying how well this network represents the physical property that we want to describe, and then we construct with this neural network E, so which is a matrix that has dimension number of output M times the number of atoms in an environment. This matrix T is given by the product of this matrix E and the matrix Q. In such a way, you see that the element of this matrix T is given by these expressions here. And you see immediately that in this expression, the permutational invariance is satisfied because the information of all the atoms appear in the neighborhood appeared as a sum. And so in this way, originally when we did when we defined initially the deep potential method, we were sorting the atoms in a neighborhood in order to satisfy the permutational invariance. But now with this 2 neural network representation, that is no longer necessary because this formulation automatically satisfies permutational invariance because all these atoms appear in this sum, and then we have to define a quantity that is invariant with respect to rotation, translation, and permutation. Already T is invariant with respect to translation and permutation. In order to define this quantity T, that is called the feature matrix and contains the descriptor of the atomic environment, what we do, we take the first M prime columns of the matrix T, and we construct with that a matrix S, and then we define a matrix D by the product of T with the transpose of S. So the matrix D is made by scalar products and is therefore invariant not only with respect to translation and permutation, but also with respect to rotation. Then from this matrix D provides the input information, the descriptor of the environment, and from these descriptors of the environment, we construct a fitting neural network that is a row matrix here with M element, and this fitting neural network is then used to construct, to obtain the Wannier centroid coordinate by multiplying this matrix, sorry, I went, by multiplying this matrix with the last 3 with the last 3 columns of this matrix T, which transform like the Cartesian coordinate of the vector that describe the relative coordinate of the atoms K in the environment I. So automatically, by this construction, this object will transform covariantly with respect to rotation. With simple modification, one can one can define with these two networks a quantity that is a scalar quantity, like the potential energy surface, or a quantity that is a tensorial property like the polarizability. And now, since we have this Vanier centroid, then we can go back to the laboratory frame and obtain the centroid coordinate in the laboratory frame. And then in terms of those, we can write down the polarization or the derivative of the polarization, again, with the example of a water system that is given in this way, where we have the contribution coming from the oxygen, the contribution coming from the hydrogen, and the contribution coming from the Vanier center. Let me, okay, so that's what we can do. And at this point, what we have to do, let me speed up a little bit. What we have to do when we have this network, we have to optimize the amount of ab initio information that we need in order to train the network, because if training the network is as expensive as performing a large number of ab initio calculation, like in an ab initio molecular dynamics simulation, there will be no advantage. We have developed an effective learning scheme that is called deep potential generator, which essentially is based on this cycle here. We use the concept of ensemble of neural network. The neural network dependence on the parameter of the network, the loss function that one optimizes when one trains a network has a highly nonlinear dependence on the parameter of the network. So if we start with different initialization of the network parameter, we get different neural networks. When these different neural networks are all equally good, they describe equally well the physical property of interest. So we use an ensemble of neural network, and we explore the relevant phase space using this neural network that is much cheaper than ab initio MD. And with this initial exploration, we do sampling and we monitor the variance in the of the physical properties of interest in the ensemble of network. When the variance exceeds a certain threshold, we label those configuration, and we acquire new ab initio data for this configuration to improve the training, and we repeat this cycle many times until we converge to a neural network representation that is good all over the phase space of interest. So this is the basically the technique that we use, and we have already applied this technique to a number of physical problems. And here I want to focus in particular on two very recent works. They are not, one is in publication, but there are two that are in preparation. And the first one, we have been able to use this neural network representation to study the property of liquid water at deeply undercooled condition. Some of you, well, you may know that water has many anomalies, and these anomalies, one model describing those anomalies is based on the existence of a critical point at deeply undercooled condition. Unfortunately, this critical point cannot be reached experimentally, and so computer simulation are very important for that. Now, let me just explain very briefly here. So what we do, we have combined the deep neural network description that I mentioned before, that was based on density functional data based on the scan functional that works quite well for liquid water, using a multi-thermal, multivariate approach that is able to provide information over an entire finite range of pressure and temperature. Now, in order to use this kind of technique, one needs to sample with molecular dynamics for several tenths of nanoseconds, which is definitely completely beyond the scale of ab initio MD simulation. So here one can see a comparison of data for a number of thermodynamic properties, the second peak of the pair correlation function, the density, the isothermal compressibility, and the diffusion coefficient, comparison between simulation and experiment. I must say that in order to achieve a rather good agreement with the experiment. For instance, here you see that there is a density maximum in both experiment and in the simulation. We had to perform a rigid shift of minus 47 Kelvin to facilitate comparison with experiment. Now, so that means that the functional is not perfect, but it also means that we are doing, these are purely classical simulation. Definitely, if we treated the nuclear coordinate quantum mechanically, that will reduce the amount of the shift. That is something that we are plan to study in the near future. Now, this is also consistent with the freezing temperature of this model that was found independently to be, that we found independently to be about 318 Kelvin. So here is the oops, sorry about that.
We have a few minutes, Roberto. Thank you.
Yeah, here, this is the bulk of the result. So these are all the data points that we obtain with this multi-thermal, multivariate simulation are given by this square, by this field square. The lines are this data that has been fitted to a simple two-state equation of state model that has only a few free parameters. With these few free parameters, we are able to fit extremely well the dependence obtained in the simulation, and this also gives a coexistence line, that is this line here, and this critical point that is over there, this liquid-liquid critical point. So this is not a proof that the liquid-liquid critical point does indeed exist, but strongly suggests that with a fully non-empirical potential based on neural network, we obtain a liquid that has all the characteristics that lead to the presence of a liquid-liquid critical point. Let me now go to the other application that I want to describe. In this application, we consider infrared absorption. So we are using this polarizability tensor. The infrared absorption is given here by this integral of this correlation function of the time derivative of the polarization. And we consider this thing now rather than at extreme, extremely undercooled condition, at extreme pressure condition. And consider ice at very high pressure transform from ice 7 to ice 10. In ice 7, you see there are still water molecules and the Pauling ice rule are satisfied, but they are not obeyed anymore as we move toward ice 10. And in ice 10, one has a structure with the hydrogen that are just in the middle of the bond. Now I report here result for the simulation obtained with our technique, the blue line, compare with experiment. The experiment is this old paper, is a fantastic paper published in Science by this group that did a diamond anvil cell experiment. And you will notice that in the experiment there are some dashed lines. These dashed lines correspond to region of the spectrum where they do not have experimental data. They measure epsilon 2 from the reflectance, and because there is strong absorption by the diamond of the anvil cell. So these are this dashed line in the experiment are obtained from an oscillator fit. But overall, there is a rather good agreement in the change of the spectrum that we obtain from our simulation and experiment. I want to discuss just the last part. Then we went to higher pressure. And that is something I'm quite excited at the moment. That higher pressure, you see, when we go to at the highest pressure here, you see here below at low pressure, there are many modes that are associated to the presence of the molecule in the system. But when we go to this system ICE10, we have essentially two modes that are strongly infrared active. If we increase the pressure, what happens, you see that there is a modification of the spectrum like in this way. So it seems that there is a mode, this mode that was at low frequency, the low frequency mode keep increasing the frequency and eventually crosses the high frequency mode that is relatively unaffected by the pressure. These two modes are called stretching and deformation mode. These are data in this range of pressure that I report here, taken from experiment, the dot, and the red dot are the results that we obtained from the simulation. So what is happening here? What is happening here is that there is a Fermi resonance due to the strong anharmonic coupling between these two modes. And what happens is that the stretching mode couples strongly with the volume, and so it is affected by the pressure. And so it increases because it corresponds to a change in volume, and so it increases the frequency with pressure, whereas the other mode remained relatively unaffected. So this is something that was not obtained before by other simulation, and has been possible with this kind of neural network. We can also predict what will happen to the Raman spectrum and other properties of this system. And this low frequency, we have data also for this low frequency that is before the transition to ICE10 that occurred in this region here. And we also here have some correspondence, rather good correspondence with the experimental data. So that just was the last thing that I wanted to show. And let me just mention a couple of remarks at the end. Deep potential molecular dynamics is significantly more efficient than DFT-based ab initio molecular dynamics. It is more efficient by several orders of magnitude, and moreover has linear scaling with size, opening the way to studies that would be impossible with ab initio molecular dynamics. I just mentioned two very recent ones that we are doing, and one can see that one can get some new physics out of the deep neural network representation. I want also mention here that recently our team, and particularly in this case Weili Jia, a postdoc at UC Berkeley in the group of Lin Lin and Lin Fong, again, always Lin Fong, have optimized very efficiently the DPMD code to run on the Summit supercomputer, achieving a performance in molecular dynamic simulation of 1 nanosecond per day for system containing more than 100 million atoms, by retaining the ab initio accuracy. So that means that there is the realm of studies that could be done only with empirical potential, but become possible with this kind of simulation. Last, there are issues at which we are working. This neural network provide a finite range representation of the potential energy surface. Long-range electrostatic effects are not included, or they are only included effectively within the finite range form of the potential. That in some, there are issues where they are important, and so we are currently working at different ways of introducing this effect. There is also the other issue is quantum correction to dynamics, quantum correction both to static, which is relatively easy, and then quantum correction to dynamics that is more difficult. But again, having a neural network representation should help, because we can achieve good statistics in the sampling of the various configuration. And then, of course, there is the issue of chemical accuracy beyond DFT, and that is an issue that will be discussed, I think, by many other talks in this conference. With that, I thank you for your attention.